Yes, hello everyone, and welcome to another episode here on Freaky Physics. And we are again going live today with another lesson. We are continuing yesterday's lesson, and yeah, I'm taking the mask off. Yes, I am wearing a mask because I have a cold again, but it's a different one this time. Um, so we're continuing with the discussion, and I am a bit late actually to the class. Let me get in there now before anything else. All right, let's join the lesson now. Okay, we're gonna start. Hi Gita, good morning, I guess.
Yes.
All right, morning.
Morning.
How are you today now?
I'm good. How are you?
Good, doing good. Thanks for asking. All right, you sent over a couple more questions for relativity. Okay, so before we go anywhere though, you understood everything we did about time dilation so far, right?
Yes.
Okay, so basically you just use the equations, but once you use the equations, all you really have to be careful with is which one is the proper time and which one is the dilated time. All right. Okay, so let's move on to the next bit. But before that, let me get here. There we go. All right. So the next thing we're gonna do now is length contraction. Okay. Again, as much as
Yeah.
I would like to go into the details of how to do this, we are a bit we're a bit short on time, so we'll just go straight to the point. Okay. By that I mean we need to cover a lot of things here. Contraction. Okay. But suffice to say for now that again,
Yeah.
L prime here, the equation here is L times gamma. Okay. Again, L is the proper length. Okay. And gamma here will be equal to 1 over root of 1 minus v squared over c squared. Okay. All right. So what does this mean again? Basically, if we go into the actual meaning of this basically means that we mentioned this yesterday. The moving for okay, a stationary observer. Okay, observer will see a moving object. Okay, object as shortened. Okay, shortened by what factor? Or rather, by the factor's already by gamma, but let's just do the other one in the direction of motion. Okay, so that's the key part here. So for example, you have this ruler here, or better yet, let's say that this is the observer, and then this is a box with dimensions L, like this. Okay, and then that stationary box with dimension L, once it starts moving, two of its dimensions will stay at L, namely these, but this part will be L prime. Okay. In other words,
For the moving object.
for the moving object. So if the velocity is going this way, or it could be the other way around. Either way, um, that's what happens. So the other lengths don't change; it just changes in the direction of motion. Okay. All right. So let's go back.
So
Go
okay.
ahead. Sorry. Go ahead.
If it changes the direction of motion, then the right L would change.
It would still be shorter, but yeah.
Which one?
Okay. So if V went that way, then it would be this L that would shorten. Okay.
Okay.
All right. Similarly, if it went up, then it would be this L that would shorten. Okay.
Okay.
All right. Let's go now straight to the problems that you've sent over again yesterday. Let's look for a for a length contraction problem first. I saw one yesterday. I think this is a good one. Copy. All right. Okay. So here's the problem. This time, okay, that's done. Okay. Um. So once we have the equations and once you understand what's happening, it's pretty simple to use the equations straight away, right? But there is this is just while the image is loading. Okay, so so we can kind of get that lengths change and times also change, or the time you measure also changed, simply because one reference frame is moving compared to the other, right? Later on, the
Yeah.
next bit there is what's going to happen if instead of just having two reference frames moving to each other, there is there's that third object now that's moving at another speed, right? Because so far our examples are we have two reference frames. One reference frame has a third object, but it's stationary compared to that reference frame, right? Later on, we'll go through what happens if there's a third object and it's moving to relative to both reference frames. Okay. All right. So let's take a look here at this problem now. At the Okay. So here at this particular instant s prime is going coincident with s when you start the stopwatch. In other words, at t equals 0, um the x coordinates, the position coordinates, we'll just call it x, okay, equals 0 for both s and s prime. Okay. All right. Now the cone is exact, well, it's already given that according to s, so to s the cone is 76.5 meters away. Okay. All right.
Yeah.
So um okay, so let's take a look first from s's point of view, from s's reference frame. Okay, so at t equals 0, the van, we'll just call it van first, is equal to 0 meters away, right? And at t
From.
equals from the observer, or we could just say from starting point. Okay,
So the van and the observer are in the same line,
at t equals 0. Okay,
but aren't they a distance apart?
they will be. The idea here is the van is moving, the observer is not, right? So basically what is happening here, let's go back here. uh it says here that at the instant s prime is coincident with s, you start the stopwatch. So in other words, when they're right at the same point, that's t equals 0. So that's what this part means.
Oh, so the answer to the first question is just 76.5.
Uh-huh. All right, so what we're looking for in the first question basically is according to the reference frame s. Okay. uh Okay, so in this case, the van is 0 meters from the start at t equals 0, and at t equals 2.75 seconds, the van is equal to v at 2.75 v meters away, right? Does it
Mm-hmm.
say what the speed of the van is? Not quite, right?
No.
No. No, it is. It's 25.75. So let's put that in here, 25.75. Okay? And that's equal to how many meters would that be? Let's put that on the calculator real quick. 2.75 times 25.75 gives you 70.8125. So let's put that as 0.81 meters away. All right. Meters away from observer. from observer in S. Okay. All right. Okay. So that's the first part. Uh, Basically, we've just solved the first part, right? However, at the same point, basically, this is going to tell you, we can do the same thing for the second one. Shall we do the second one now? No, let's not do the second one yet. But here, let's go to the first one. It doesn't actually say what the question is, but from the way it looks like, the next question is what is x prime? Okay. All right. So let's take a look at at this. What is the value of x prime at t equals 2.75 seconds? Okay. In order for us to do this now, we just basically look at this. We can just say that here, let's put it in the diagram first, that the person, or that the van traveled that how much was it? 70.81 meters here. So let's label that here. Okay, and we know that the total total distance is 75.6. So if we take away that value from 76.5, this distance is going to be 5.69. That's the x prime. Okay.
Right.
Okay. So according to x prime is equal to 5.69. Okay. So according to S, x prime is equal to 5.69 meters. Okay. But how about for the van, for S0 now? Okay, for S0, for S prime rather, let's use S prime here. We're gonna have to take into account that x is gonna be shorter. So what we're gonna do now is x prime. Okay, I used the wrong symbol here. So let's just say 0 for here to make it easier. Okay, so S0 would be this van. Okay, this will be x0 prime, and that will be equal to x prime times gamma. Okay, so now we're gonna put that in. Okay, so what are we gonna put in here? Because this is not a relativistic speed, this is a very small speed. We will actually see that it's gonna be very approximately equal to x0 prime. Okay, so let's take a look at the value again. That's 5.69. Our x prime is 5.69 meters. Our gamma is 1 over the square root of 1 minus, what's the speed of the van? There, 25.75. Okay, but look here, 25.75. Let's remove the bracket here. But if you compare that to C, we're gonna square that, but C is gonna be 3.0 times 10 to the 8, and then you're gonna square that further, right? So just imagine that this is 10 to the 1, that's 10 to the 8. That's like a 10 to the, that basically gives you 10 to the 7 in the denominator, right? So that's gonna be, let's just do it like this, 5.69 meters times 1 over church bells.
Yeah.
All right. Okay.
Should
Let's.
I mute maybe?
That's fine. I kind of miss hearing church bells. All right. Okay, so let's go back here. So let's just actually get that value. So 25.75. Oops. I'll just put that in the calculator. 25.75. Just square that. Or better yet, let's do it the other way. 25.75 divided by 3 raised to 8, and then square that. Okay, so basically that's a negative 4.88 times 10 to the minus 12. Okay, and then we're gonna do the final part. We're gonna subtract that from 1, and then we're gonna, oops, I forgot the square root sign. So let's take the square root of that. Oops, I forgot that. Okay, so 4.88 raised to negative 12 is that, then minus 1. Okay, don't forget to remove the negative sign. Square root that, and then flip that over. That's still gonna give you basically 5.69 times, I'm just gonna put the number, the whole number, to the first non-zero digit here. Okay, so 1 2 3 4 5 6 7 8 3 6 9 11 zeros. 1 2 3 4 5 6 7 8 9 10 11 2. So you will see did I do that right? Okay, I think I missed something. It should be over. That should be divided. Okay. All right.
Right.
All right. But either way, that's the answer. Basically, you divide that by that number. That's still basically 5.69, right? So let's
Okay.
just put that 5. So 5.6899. Okay. So it's still gonna be by a very tiny amount. 6, 8. Then let me just count how many nines that is. 1, 2, 3, 4, 5, 6, 7, 8. 8 nines afterwards. 6, 7, 8. Then another 8, 6, 1. There. Meters. So basically, yeah, that length contracted, but it's gonna be very tiny compared to what we actually see. Okay? So we just say it didn't contract because it's moving at such a slow speed compared to light, at least. Okay?
Okay.
All right. So that's basically how you do length contraction. So let's see. Is there anything I need to correct here? Yes, there is. I'll just need to correct this part. Okay. Okay. So that's length contraction. So again, equation wise, pretty straightforward. You just need to know which one is which, right?
Yeah.
Okay, let's get on with another problem. This time it's about let's do that at the end. Okay, now let's do this next part. This is now about space-time diagrams, or Minkowski space-time diagrams. Okay, all right.
Right.
Okay, so I bet this is the one that kind of confuses you, right? Really
Yeah. I
confuses you.
completely missed. Really complete. I completely missed this lesson.
I
So
see. Okay. What kind of graph do we see here? All right. So for short, we usually either call them Minkowski diagrams or space-time diagrams. Okay. But the full name is the Minkowski space-time diagrams. Okay. Now, let's take a look at something first, just so it's easier to understand why we can do the diagrams like this. Okay. So let's go back to L. That's gonna be L prime. That's gonna be L divided by gamma, right? And then if we
yeah.
look at time, let's see, t should be equal to t rather. T prime should be equal to t gamma, right? Now, here's the thing about the Minkowski spacetime diagrams. We can actually say that this is C here, this is C here. Okay?
Why see?
Why? Because that makes it easier to graph. Because here, okay, let's just say that this is T and this is L for now. for now. Yeah. So if I do this line, I could make any line like this do this, and I could say that any of these lines describes light speed. Okay. Light speed. Okay.
In terms of time and length?
Yes, in terms of time and length. So basically, how do you get the speed of light here? That will be this length over the time. And if you think about that, that's the inverse of the gradient. I'll just use the word
Yeah.
gradient, right? Okay. Now, that's a problem if we do it with with t only, all right? But once we put c in here, there is only one speed of light that will work. Okay, because we know that okay, because we know that so if you find the gradient here, so let's get rid of this first, and let's get rid of these guys first, yeah? So if we do the same idea and we find the gradient here will be equal to ct over L, right?
Yeah.
Okay, so that basically means that that C is equal to the gradient times L over T. Okay, this kind of makes sense now because all of a sudden we can find this line, yeah? There is only one line wherein this V is equal to C. This L over T, this can be V, right? So I'm just gonna change that into V, since L over T equals V for now, right? The gradient times V. So so what happens here? If V equals C, then the gradient equals 1, right?
Okay,
Okay.
but if we wanted this relationship, wouldn't it be enough to have T and L plotted? Why does it have to be
Okay.
CT?
Because if we don't put that C in there, we will not have C in here right away. So all we're gonna get now that the gradient, all we're gonna get here is that the gradient times the velocity is equal to 1, and therefore the gradient is just 1 over velocity. But there's no special case. You see what's happening? If the gradient could still be if v equals c, then the gradient is still 1 over c in this case, right? Now,
Yeah.
that basically means I can, how can I draw this? 1 over c is the gradient. I can actually just, that's gonna be basically it, or that's gonna be it, which is, again, as you pointed out, perfectly reasonable, right? Now,
Yeah.
the reason why we want that C in there and we're gonna put the C back in is because this makes a 45-degree angle between both axes. And that's gonna be very convenient for understanding what's happening. Okay? What's so special about that 45-degree angle? Because we can draw another line like this going the other way. This is V equals negative C in this case, right? And what happens here? If this is 45 degrees, you will notice something. What angle is that thing in the middle? 90.
90.
That makes it easier to understand what's happening. Okay?
But why do we need the other side and the angles?
These angles, why do we need the angles? Because it's gonna make it easier to convert between two reference frames. If we're talking about just one reference frame, we don't really need to put C in there. Okay? But once we have two reference frames, it's gonna be easier to see it in terms of what's happening once we have the two reference frames, because of the fact that that's gonna be at 90 degrees over there. All right? Okay. Okay. This is what I mean now. We'll get to I'll kind of draw it here and again, but this time around, so what is the space? I'll use space-time diagram. I'm more comfortable with that time. With that term. Okay. Space-time diagram 1. S according to S. Yeah? It's boring. This one's boring. But it's going to be important for us to to do that so that's easier to see. So remember, this is X, and then this is CT, right? So we're going to draw that this line again. Again, this is V equals C, right? So that's for light. Now, for a stationary observer, what's happening? Are you actually moving position? Because according to S, according to you, are you moving? You're not, right?
Uh,
So what's your
no, if I'm stationary.
so if we're gonna plot that as points, that's basically how that would look like. You're only traveling through time, but you're not traveling through space. So um that's basically your graph. And this graph is called your world line. Okay? So this world line is for S according to S. Okay? Okay. Now I'm gonna draw another possible world line. Now, think about it this way. Is it possible for this world line to exist?
World line is only traveling through time.
No. A world line can actually has to travel through both space and time. But it can travel only through space or it can travel only through time in certain cases. But most of the time, it travels through both. Okay? So,
Right.
all right. So this is gonna be S prime's world line according to S, right? Okay. Now, you notice something though? You notice something? This makes a certain angle theta here, right? Don't
Yeah.
worry, we won't go too much into the math behind it, but you notice that there's this angle theta here, right? Now, what I'm gonna do now is I'm gonna draw a new set of coordinates according to S prime. Okay, so S primes. Let's do it again. Space-time diagram according to S prime. Okay. Now, according to S prime, and here's the weird thing. Don't worry too much about it. It's gonna make sense once we actually turn it into something we're more familiar with. But now, we're not gonna look at something familiar. We're just gonna look at what this says here. So that's gonna be the world line of S prime, right? Okay. Now, you notice I didn't draw the axes yet?
Yeah.
Okay. I'm gonna draw that theta here again, and now I'm gonna draw an angle theta here. Okay. I'm also gonna draw that world line for the light. So this is still V equals C, right? And you will notice. Okay, let's not do that other angle. Let's just keep it like that. Yeah. Now the space-time diagram according to S prime will also be. So here's the idea. I'm gonna use red in this case. I'm gonna draw another line like this. Okay, and that's also gonna be theta here. Okay, the reason for that happening is a little bit complicated, but it has something to do with the idea of this, that the factor gamma changes both L and T. All right. So what basically, so according to S, this is S prime's spacetime diagram, but also remember that according to S prime, he is stationary, right? S prime is stationary relative to S prime, right? Relative to S prime.
Yeah.
So that's why we can draw this line right here. Okay. Okay, that also means that this angle here, it kind of changes the way it looks like, because now we can draw a few coordinates here. Earlier, we can basically draw the coordinates just by following these vertical and horizontal lines on the grid, right? But here, what we're gonna do is we're kind of gonna do a kind of weird thing about the coordinate system. It's gonna look like that. You get why it's like that though, right? Because these these coordinate lines should be parallel to their axes. So the other coordinate line here would be, let's use this. This is gonna be the x prime, right? Uh, is it x? Yes. This is gonna be t prime. Okay. So what's gonna happen here? We're gonna do something like that. You see how you see what's happening here now? It's kind of weird, but it makes sense, I hope.
Uh, right. So this graph is in terms of s prime,
Yes, this graph is in terms of s prime. All right.
and what is the point of these lines?
Well,
The green ones.
here's the thing. The green ones are all parallel to the t prime axis, right?
Right.
And
Yeah.
then the blue lines are all parallel to the x prime axis.
Yeah.
Okay.
And what does that do for
Well,
us?
for us in for the person in s prime, nothing, because later on, nobody in their right mind in s prime would draw their coordinates like this, right?
Right.
Right? In s prime, they would actually draw their coordinates like this. So this would be t prime, and this would be x prime, right? But you will notice
Yeah.
something here. What happens to the spacing of t prime here because of this angle? What happens to the spacing? It shortens out, right? So
Yeah.
basically instead of following this, we kind of have to go below this once it gets stretched out like this. So the spacing is now shorter. Okay. Similarly, what happens to the x prime coordinate compared to x? That x prime coordinate is longer, right? So our markings would are not gonna be here anymore. Our markings will be a bit longer. So something like that. Okay. But here's the thing though. Remember remember the line for light. That's still not gonna change. That's still gonna be 45 degrees. Okay. So this angle according to S prime will still be 45 degrees. Okay. So that's what's happening with space-time diagrams. But okay. It's not so useful yet, but are you kind of getting the idea of what to do?
I'm just confused. Like, what do we need this
All right.
for?
Let's remove we'll get to that in a while. But so far, does it make sense about what's happening to the stretching and squeezing off the time and x prime, t and x prime, t prime and x prime? Is it kind of clear? Because
I guess
I'm pretty sure it all doesn't make sense, right? So
it's just, yeah.
this is what we'll do. This is useless when it's just two things, right? It's just s and s prime. So now we're gonna put s and s prime together with a third object. Okay. Now we can actually do the calculation there, and that's what we'll do to verify what we're doing. But let's do this now. We have the space-time diagram with a third object. Okay. Okay, this is where this becomes quite powerful. Okay. So again, this is in terms of s. So this will be t, and this will be x, right? And of course, don't forget to draw the 45-degree line for light, v equals c. Okay. Now let's draw three world lines. Let's do an s. This is s, right? Let's draw a world line for s prime like this. S prime, and this time, let's draw an event. Okay, because space-time diagrams are actually event graphs. They're not position graphs, they're not time graphs, they're event graphs. Okay, events are basically anything happening in space and time. So if you kind of think about that, that's the exact definition of an event, right? Something happening somewhere at a certain time. Okay, so let's say that in this case you have this event here, and we'll call this event E. Okay. All right, and let's draw the world line here for this event E. Okay, let's use pink for that. Okay, now let's keep it easy. According to S, okay, let's just say it like this first. According to S, E travels, let's just say it as 1 here. E travels 1 unit in sorry, that's CT, in time. That's just 2 CT, right? In time 2 CT according to S, right? So far clear, right?
Yeah.
Now what we'll do now is we're gonna do the trick earlier with drawing all those parallel lines to S prime like this, and drawing this other thing here. Let's use this. So this will be, let's do this as yellow. Again, this is gonna get a bit confusing if we don't label stuff. So this is gonna be our T prime, right? And then this other line here will be our X prime, right? So what we'll do now is we're just gonna draw that. Oops, sorry. How is that gonna look like if I draw that? Okay, something like this. Okay. So according to this, our coordinates are basically for ER where we have our coordinates for X to be there, and we have our coordinates of Y to be somewhere here, right? Okay, it's not so clear yet because we only have a few lines, so let's not use yellow for the X prime. Let's use this blue. Okay, so if we do that more or less like so, and then let's use yellow again for this time T prime, right? So T prime gonna be like here. Okay, so this thing, where is it's kind of not clear, but let's zoom in a bit. Let's see if we can figure out what's happening before we actually turn it into the T and S prime coordinates, right? So what's gonna happen here is where's our line? This is our line, initial line, right? Okay,
Yeah.
according to S prime, our event is here, and this event is happening at, well, where is that? It's going to be somewhere here on the S coordinate, and then on the T coordinate, and then on the X coordinate it's going to be uh somewhere here, or somewhere here. Actually no, it should be somewhere here. Okay, so again, just looking at it without any calculation yet, this already tells us that there's something different with with E according to S prime. It doesn't happen in 1 unit in the time. It doesn't travel 1 unit in the time to CT. Okay, it travels a bigger length in a shorter amount of time. Okay, now what's gonna happen here is this basically tells us now that in S prime, E travels X prime, which is greater than 1 unit, in T prime greater than less than, rather, less than 2 CT units. Okay, all right, and then from here we can actually use the what's this, we can use the transformation, the Lorentz transformation, to calculate what the actual values for x prime and t prime are. Okay. All right.
From
Okay.
this graph.
Yeah, from this graph. We can kind of tell from this graph, but again, it's not very clear yet what exactly is going to happen, right?
Wait, sorry.
Okay, go
I have a
ahead.
question.
Go ahead.
Um, okay, so we plotted this graph, but how do we know how to draw the lines for each, like the S prime and S?
Okay. The S prime, oh, sorry, let's start with S. One of those, so one, usually S, yeah?
Yeah.
Usually S is automatically the normal grid, okay?
Which is?
Which is basically the grid we would do like so, like this. Okay. All right.
Yeah, but like the gradient and
Uh-huh.
like the way we draw them, is it just random or is it?
Actually, it's not
Within
quite
the-
random, okay? Here's the idea. And then this is S, right? Sorry, this is CT, and then this is X. So again, this is V equals C. Now, what do you draw here? The next drawing here would be this. Now, one thing about this is this will always lie between this. Okay, not always, but for um all physically valid events, they're
Mhm.
always gonna be between the CT and the V equals C lines. Okay, this can happen, but I'll just draw this here. This can happen, but this does not mean anything physically that we have observed yet. We'll get to what that means in a while. Okay.
So as long as it within the V equals C and CT, it's correct.
Yeah, that's correct. And then the second thing about this thing is about this line is that the gradient equals 1 over v, the speed of the object. Okay.
Okay.
All right. What else? So that's the second part. All right.
And the other line is under.
Yeah. Then we can, all the lines we have to draw are gonna be here, something like that. Okay.
For both observers.
Yeah, for both observers. Now, okay. Now the other part here is what happens to the other one, right? So the other one. So let's say that let's draw a third. Let's draw another line for S prime. Let's draw the S prime to be like this for now. Yeah, that's S prime. Okay.
Yeah.
That's S. Now the other one, usually S prime. Okay. Okay. In the unadjusted graph. Okay. Okay. We will have to draw this again. So for example, let's put it back. This is S prime, right? Okay. Now the CT prime CT prime axis coincides with S prime's line, world line. Okay, that's the unadjusted first, so it will coincide with so I'm just gonna draw it like this so it's easier to see. So this is
But
your
I thought they're like Y, X and Y.
Sorry, say that.
The CT and
Yeah.
I thought the CT and X are like X and Y straight
Yes.
up.
Yes, that's the idea. But the idea here is, again, we're drawing the lines according to what S would see, and then later on we adjust it according to what S prime actually sees. Okay?
Oh,
All right.
okay.
So this is gonna be your CT line, like so first, yeah. Now the other line we need to draw here, we still need to draw that V equals C line, right? But the idea now is whatever this angle is, okay, that's gonna be the same as this other angle. I'm gonna draw another set, another, let's not use red, let's use orange in this case. Okay, we're gonna draw another line like this, and this is also gonna be theta. Okay, and this is gonna be your x prime axis. Okay, so
Yeah.
the x prime axis subtends an angle, subtends the same angle from x, okay, as ct prime from ct. Okay, all right, so that's the idea now. And then of course all the other grid lines will follow. Let's just put that last part. All other grid lines will follow these lines. Okay, all other grid lines follow this. Okay, so the idea now is let's use yellow for this bit. So my grid lines will on the x prime would be something like that. And then for the other one, let's use that. It's gonna be something like that. So you see the grid lines, they're not exactly 90 degrees yet. Okay, and then the last thing that will
Yeah.
happen here is that all okay all events will now follow these lines. Okay, according
And the distance between them,
to
how much
yes.
is it?
Now the distance between them, that's a very good question. The distance would actually lengthen. No, it will contract rather. The distance will contract, but the time will lengthen. Okay. Okay. So how do we know that? So if we zoom in again, so we know that this is our CT prime graph, right? So look here, going from here to here, these same basically the idea now is the distance between this point of the line and this point of the line, it's longer. That corresponds to time dilation.
It's longer than the usual graph, the
Yeah,
normal x and
the
y.
normal, yes, it's gonna be longer. So similarly on the on here, you will see that from here, okay, I didn't draw it very clearly, but if I drew it clearly, it should be somewhere here. Okay,
Okay.
it should be something like this. So you will see here that these 2 points are a bit shorter compared to these 2 points. Okay.
Yeah.
All right.
And how far apart do we draw the lines? Does it matter?
It shouldn't really matter. It shouldn't really matter, but yeah, it shouldn't matter at this point, because the way to do it properly is we still have to use the Lorentz factors, the Lorentz factor, to see how far apart those lines actually are. Okay.
Yeah.
All right. But either way, what's gonna happen now is, so let's kind of look at, here's a question that is similar to what we've discussed and that you sent over. Okay, so okay, so here's to show that the Lorentz transformations work for a point located at x equals t in. Okay, so according to this, let's look at this briefly. So this is an example of what I mean. You see that this thing, this is CT. This is the S prime. This is the S reference frame, right? Now you see here on this other one here, the one that's a little bit askew. You see it's kind of compressed but stretched at the same time.
Yeah.
Okay, so what's happening here is, okay, so let's take a look here. Where's that word line? Okay, this thing here, that's V equals C. And in both cases, remember that C is constant for both cases, right?
Yeah.
Okay, so what is happening in this graph, according to this, x equals 3, so this is x, This is CT, right? Okay, so what are we gonna do? Explain that to. It's not so clear what the actual question is. Okay, let's just do it either way. Uh, okay, according to this, what is the x value here? This is x equals what?
3.
3, right? And then this is CT equals 2. Now, what are we gonna do? We're gonna look at this according to our new coordinate system. Now, this new coordinate system is now accurate. It's not just, I didn't just draw them anymore. They're now accurate. Okay, so that's x. So let's take a look at the prime values. So where's our x prime axis? That's our x prime axis. Okay, so what's x prime here equal to? So take a look. It's here. So according to this is gonna be 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14. This is 14 little squares. 14 little squares would be 2.8, right? X prime will be 2.8. Okay. Now
Yeah.
similarly, let's take a look on the y coordinate of this thing. The y coordinate is gonna be here. To be more specific, the CT prime. That's our CT prime axis, right? So we're more interested here. So this is CT equals 2. So again, 0.2 on each. Let's count. 1, 2, 3, 4, 5, 6, 7. That's 8. So our CT prime equals 8. Oh, sorry, that's 8 squares. So that's going to be 1.6, right?
Yeah.
1.6. All right. So what just happened here is this time dilation, and this is time dilation, isn't it? In a different kind of manner, right?
So
Now, okay,
time
go ahead, go ahead. I see some.
is
Yes.
I understand the graph, but what does this tell us? Is time dilation for one for the like S or S prime looking at themselves or
No.
looking at the
Time dilate. Okay, so both time dilation. Both of them. That's gonna be both for time dilation and length contraction. Okay. Length contraction. Both of these will work. Will only be um as seen from S. In this case, S. Okay. So what does this mean?
for
This basically means if S observes this from their reference frame, it's going to take 2 seconds and 2 and 3 respectively for CT and X. But if they look at this, if they're stationary but our object is moving at this speed, whatever the speed is, then S will observe at CT equals to 1.6 and will observe an X equals 2.8. In other words, it shortens, but the time, did I do? Yeah, the time kind of shortens as well, right? Now, in this case, you may be wondering, why did both shorten? Don't we always say one will increase, the other will decrease?
yeah.
I'll tell you why. Look at where our event is. Is it above or below the C equals V line?
One of them is above, the other is below.
Okay, remember this is always the C over V line. It doesn't matter which reference frame we're looking at. Okay, again, that's C V equals C. So in this particular point, this event is below the C equals V line, right?
Oh yeah, sorry. Yeah.
Okay, and because of that, this tells us one thing. This is traveling faster than light.
Right.
So it kind of breaks our expectations. Okay. Okay. Now, what's the Lorentz? So we can actually kind of see what the Lorentz factor here is. It's gonna be, what's the Lorentz factor? In this case, x should be equal to, x prime should be equal to x times over gamma, right? So gamma is equal to x over x prime, and that's gonna be equal to 3 over 2.8. Okay, let's calculate that real quick. 3 divided by 2.8, that's gonna give us a Lorentz factor of 1.07, which we don't normally get.
What's the usual range?
Hold on, let me, oh yeah, this is correct, never mind, this is still okay. Yeah, so will we get the same gamma here? Will we get the same gamma here? Remember, what do we have? So t prime should be equal to t over gamma. Oh, sorry, t gamma, right? So in this case, gamma equals t prime over t. Let's see if we get the same answer. Our t prime is 1.6, our t is 2. Does that give us the same value? No, it gives us 0.8. Okay, now here's the thing though. 0.7. All right, so okay, so in this particular problem, Lorentz transformations work for a point located at. Okay, we're supposed to show that it works, right?
Yeah.
Okay, so is there something I missed? Okay, let's take a look again. 1, 2, 3, 4, 5, 6, 7, 8, and then 2, 3, 4, 5, 10, 14. What's 14 out of, okay, 14 out of 15 times 5. Okay. Okay, let's just do that. 14 over 15 times 5. 4 and 2/3. Alright, I think I see where they make this. This should be 2.67. Okay. 2.67, but that still gives us a value that's incorrect. Okay, I'll see where we went wrong here in a while. I'll let you know as soon as I can. All right.
All right. Just one thing.
Go ahead.
Could you share the boards like from last time and this time?
Yeah. This is actually the same board, so I'll share that with you now.
Okay.
Okay.
Thank you. But if it's the same one, even I can find it in the chat.
Right. Okay. So I'll just share it with you now. Okay.
Okay,
All right.
thank you very much.
Okay. The rest of the problems later, we'll go through them once we kind of clarify everything now. Okay.
Okay.
All right. Anything else you'd like to ask before we end for today?
Just if I were to book a lesson tomorrow, would you be available?
Tomorrow, let me check something because I have another one, and I have another lesson, but I'm not so sure whether it's not consistent. It's sometimes on Monday, it's sometimes on Wednesdays, so I have to check. Yeah.
Okay, if you're not sure, I can just book it on the weekend.
All right then. Okay.
Okay.
I'll let you know as soon
you.
as I have information. All right.
Okay.
All right. So
have a good day.
You too. You have a good day. I'll see you next time. Okay.
Yeah.
Bye
Bye
bye.
bye.
All right. Where are we? Okay. That's the thing with relativity. It doesn't always play nicely with the rules. Okay, so we'll end the stream here for today. It's still for me, I'm not so satisfied with that result. So once I find a better way to explain it, I will be redoing this series. Yeah, this lesson. Okay. So anyway, for that, we'll end it here. So don't forget to like, share, subscribe to the channel, and we are on YouTube, Facebook, Instagram, TikTok and Twitch. And again, soon we'll be doing some. I'll be um, what's this? I'll be looking at options on how to make these a bit more streamlined. And once we do that, I hope that it becomes better for your experience. Okay, so with that, I will end today's stream. So that's a good morning, good day, good afternoon, good evening, good night, wherever you are in the world. And stay freaky, everybody. Bye bye now.